So today we're going to talk about the next section, which is all about symmetry. And in this course, we're going to talk about three kind of major types of symmetries. So the first type is symmetry with respect to the x-axis. So visually, what that's going to look like is something like this. And again, when I say WRT, I'm just abbreviating the phrase with respect to. That's a fairly common mathematics phrase and a pretty common abbreviation. So again, I'll just use WRT as with respect to. You're free to use that abbreviation, or you can write it out longhand. Either one is fine. Doesn't matter to me. If it's any of these kind of abbreviations that I use in class, you're welcome to use as well, unless I tell you otherwise. But yeah, so if you look when we say reflection across the x-axis, basically if I take one half of my graph on, say, the top of the x-axis, and I reflect it across the x-axis, it would lie exactly on the other half of the graph, is kind of what we mean by symmetric across the x-axis. Everybody okay with that idea? You can think of the x-axis basically as a mirror, and the two sides are reflections of one another. To tie this back to geometry anyways, we talked about reflections and rotations and stuff in your geometry course. I know that was a long time ago, but we'll continue to reference it. It's a pretty fundamental course that has a lot of overlap here. I wouldn't expect you to have any of these things memorized. I'm just hoping that you kind of remember what some of this stuff is when we mention it. It's just kind of trying to build a little bit of connection and foundation. The second type is symmetry with respect to the y-axis. So again, we'll kind of draw a picture of what we mean by that. But I'm betting that from the previous example, you'd have a pretty good guess as to what that picture might look like. So I just drew the graph of y equals x squared. Again, if you take one half of this graph and reflect it across the y-axis, it would give you exactly the other half of the graph. Or you can think of the y-axis like a mirror, and you're getting, like mirror images on either side of the y-axis. Everybody okay with that one? Okay. The third one we call 180-degree point symmetry with respect to the origin What does this look like? Something like that. So the reason we call this like 180-degree point symmetry with respect to the origin is, say we're going to take this part of our graph, we like anchor the tail of it on the origin, and if you rotate that graph 180 degrees, or the end is kind of anchored to the origin there, it would lie exactly on top of the other part of the graph. Alternatively, you might notice that if I perform a reflection across the x-axis and then a reflection across the y-axis, I would get the same result. And you could do those in either order. You could go x then y or y then x. If you perform those two reflections successively, you'd end up with the same thing as a 180-degree rotation. Is everybody okay with that idea? Okay. So, with what we've shown you right now, how would you check to see if something had one of these symmetries? If I asked you, is this, what kind of symmetry does this function have? And I just give you the function. What would you want to do? Look at the graph, right? That's an easy initial standpoint. Now, what if it's like really close but not exactly symmetric? Would you be able to tell the difference just by looking at the picture? Probably not, right? Let me show you just a little quick example of what I mean. Anytime. There we go. So let's say that the right-hand half of my graph is just y equals x squared. And the left-hand half of my graph is 0.9 times x squared. If you just look at this visually, does this looks pretty symmetric, right? If I go and actually perform the reflection now, you can see that actually, just get those grid lines out of there, actually they're not symmetric, right? It's very close, but when I actually reflect it across, you can see there's two distinct lines there. They're not lying right one on top of the other. Can you guys see that? So as helpful as kind of using our eyes is, it can be really deceptive. We'd like a better way of checking the symmetry on something other than just relying on looking at the picture. Preferably, we'd like to be able to algebraically check. So that's what we're going to do. So, if I'm looking at something that's symmetric to the x-axis, algebraically what this means is that f of x should equal negative f of x. Worth noting, something that's symmetric about the x-axis, can that be a function? Can never be a function, right? By its very definition, it would have to fail a vertical line test. Of course. No problem. In the second situation where I have symmetry about the y-axis, we have a special name for these kinds of functions. We call these even functions. And algebraically what we need to have is that f of negative x equals f of x. And for this third situation, this has a special name. We call these odd functions. And algebraically what we need to have is that f of negative x equals negative f of x. So, just to rehash here before we move forward. So if we're symmetric about the x-axis, we need to check to see f of x equals negative f of x. To check to see if we're symmetric about the y-axis or even, we have to check to see f of negative x equals f of x. And if we're 180 degree point symmetry with respect to the origin, or odd, we need to check to see if f of negative x equals negative f of x. So, let's do an example, or do some examples of actually doing this checking. So this example I've asked to prove that the following functions are either odd, even, or neither. So the first one we're going to look at is x to the fourth plus 1. If I were to start, I'd really want to have an idea of what I'm trying to prove. Because if this function is, for example, even, and I try to prove that it's odd, that's not going to work out really well for me, right? Ideally, I'd like to know kind of where to go. So what could I do to kind of get an idea of which one of these three options I should be shooting for? Leone? Graph it! Exactly. So that's what I would start by doing. So if I do x to the fourth plus 1, I just look at the graph of that. Yes, Adam? I don't. Do you need to go to the bathroom? Go ahead. So if I look at this, this looks like it's which one of those three? Even, right? Looks symmetric about the y-axis. So I'm going to write that I claim that this is an even function. So to prove that, I want to show that f of negative x equals f of x. WTS is an abbreviation that I'll use commonly. It's just short for want to show. Again, you're free to do that abbreviation, or you can write things out longhand. Either way is fine. So, what I'll do is I'm going to start with f of negative x. And what that is telling me to do is to take everywhere where there was an x and replace it with a negative x. So I'll just, like I would do evaluate the function for like f of negative 3, I'm just going to do kind of that same idea. Now I can simplify negative x to the fourth. What does negative x to the fourth simplify to? If I multiply 4 negatives, I get a positive, and x times x times x times x is x to the fourth. Everybody agree with that? And I notice that x to the fourth plus 1 is exactly f of x. So I'm done. That little shaded box at the end of my proof is just an indicator to the reader that the proof is now finished. Right? I claimed that it was even. To show it was even, I need to show that f of negative x equals f of x. And below I did just that. So I'm done. Everybody happy there? Let's do another. Let's say we want to Yes, Maya? Of course. Check to see if g of x equals 2x to the third plus 3x is odd, even, or neither. So, just like we did for the first one, first thing I'm going to do is go ahead and look at the graph of this to get a feel for which one of these three options I should be shooting for. If I hit graph and take a look at it, there's my graph. What does this look like to you guys? Odd. Good. So I will claim that this is odd. So to show something as odd, I need to show that f of negative x equals negative f of x. I guess in this case I shouldn't say f's though. What should I say? G's, right? We named our function g of x. Those should probably be g's. Gee whiz. Wah, wah, wah. All right. So we'll start the same way. G of negative x. So I'll go ahead and make that substitution and replace all my x's with negative x's. Now I'm going to simplify. Negative x to the third is negative x to the third times 2 is negative 2x to the third. 3 times negative x is negative 3x. Everybody okay to there? I notice that each of those terms contains a negative. If I factor that out, I have negative 2 times, or negative the quantity, 2 times x to the third plus 3x. I notice that this is exactly my g of x. So I have negative g of x, which is what I was hoping for. Quick question. On this step here, I only factored out a negative sign. Why didn't I take negative x out? I could have factored out a negative x, correct? Why didn't I do that? Why didn't I factor as much as I could? Ben? Good, yeah, so because I'm looking for negative g of x, all I'd ever want to take out is a negative sign. Yep, exactly right. Everybody okay with that idea? Okay. Hi. Thank you. James, pour vous. That's French for you. I don't know. I don't think so. It doesn't say now. Okay. One more. What do you think this one's going to be? Yeah, by the fundamental theorem of mathematics examples, if there's 3 options and you have 3 examples, it's probably a good bet you're going to see one of each of those cases, right? Since we've done odd and even already, probably going to be a neither. Let's just check with our calculator, though, to make sure. So if I graph this fella, well, I don't have a very good picture here. Let's make that y max a little bit bigger. Oops. Maybe make that 20. That should be enough. Okay, so if I look at that, it's not quite even. Notice that one side has a little bit more graph on it than the other. Everybody observe that? So this is indeed going to be a neither situation. So to show it's neither, oops, we're not dealing with F's or H's, I need to show that it is not odd and it's also, oops, sorry, that's even, not even, and also not odd. So I need to do two things. Everybody okay with that plan? So neither is everything else. So all I have to do is show that it's not one of the special ones. It's just some other thing. So we'll start the same way. I'll start with my negative, or h of negative x. So I will substitute in negative x for all of my x's. If I simplify that, I get 4x squared plus 3x plus 9. If I compare these, are they the same? Nope. What's different? Yeah, the sign on the 3x is different. That's all that's different, but that's enough. All they have to be is different. Doesn't matter how slightly different they might be. That's enough to show that it's not even. If I take that 4x squared plus 3x plus 9, and I take a negative sign out of it, I would then want to compare this to h of x. Is that the same? No, right? What's different? We have the sign on the 4x squared is different and the sign on the 9 is different. Everybody agree with that? So this definitely is not negative h squared. Or I'm sorry, negative h of x. So we're done. Everybody okay with that idea? The neithers are a little bit tricky because you got to check two things, but basically all you need to do is plug that negative x in and simplify, and then just make sure that the result isn't either one of those two possibilities, which is not hard. Any questions about this symmetry stuff? Okay, should be relatively straightforward and not too bad. I know everybody gets bent out of shape when we start using the P word, but these proofs are pretty straightforward and not too difficult, right? Since you're doing the same thing, you don't have to use any like theorems or anything. We just, a couple of definitions. The next topic we're going to talk about are asymptotes. Does anybody remember the definition that we give for an asymptote? Or definition-ish? Anybody remember how? Allison? Yeah, that's pretty darn good. So it's a line that the function doesn't touch, but it can get very close to. So I'm going to phrase this as an asymptote of a graph is a line. Ooh, that is none look like the word line. That the graph, I'm going to say approaches is the verb I'm going to use there, but never touches. And again, this is a fairly soft definition for something. When you take this class, you'll get a much more rigorous definition of what we mean by approaches, because that's not entirely clear how you would show something approaches, like how close does it have to get to be able to say it approaches. is an interesting question, which you'll define specifically kind of what you mean by that in a calculus course. So you have that to look forward to. So this is a fun course where we're both looking forward and looking back so often. Like I think every time we've spent, or every class we've spent a lot of time talking about things that we saw before in geometry, algebra 3, 4. And I think we've mentioned things to look forward to head into when we talk about calculus later on. A little bit more looking back right now than looking ahead, but it's still kind of a neat course because of that. All right. So we've talked about asymptotes last year in our Algebra 3-4 class. What are the different types of asymptotes we've seen? Brockton? Good. So we have vertical asymptotes. That's certainly one of them. What else? Horizontal, there you go. And there was one more type we mentioned. We didn't spend a ton of time focusing on this third type, but you saw in second semester of Algebra 3-4, Ben? Yeah, slant asymptote or oblique asymptote. Those two terms get used kind of interchangeably. For right now, we're not worried about slant asymptotes. And if you remember back into your Algebra 3-4 class, this horizontal asymptote situation was kind of tricky because we saw some rational functions that had horizontal asymptotes and some that didn't quite have horizontal asymptotes, but they were kind of close. What do I mean by they were kind of close? Let's look at this example here. So let's consider this rational function. Jeepers creepers. Quit making typos. So if I drew for this, I could do this on my calculator also, because I want to be able to write on this. It's just a little bit easier for me to just draw it in by hand, but this is definitely something that, oh my goodness, I pressed that way too many times. Definitely something that you could graph with your calculator. Oops, I drew that in the wrong direction. My apologies, I keep doing this. Let's be going that way. So if I look at this, we definitely have two vertical asymptotes, right? But with the definition we used, is that a horizontal asymptote? Jackson, you're shaking your head no. Why not? Well, we have this guy. Is this a horizontal asymptote? That horizontal dashed line. The answer is no. Leonie, you shook your head. Why not? Yeah, so we have a spot where it's crossing, right? If you recall back to our Algebra 3-4 class, we had a bunch of stipulations about like how to check to see if it was an actual horizontal asymptote or if it was just an end behavior where we might cross somewhere in the middle, but the ends of the graph behave asymptotically. That's a fun word to say, by the way. For right now, we're not going to worry about the difference. So when we say horizontal asymptotes, we're also going to be, at least for right now, talking about things like this that we've just drawn. So we're going to lump that in there. I'll let you know when we have to start differentiating, but it's not right now. We can just think of them all as kind of the same thing. Is everybody okay with that idea? Technically, what we've drawn here is an end behavior. But we don't need to be so specific as to differentiate that. I would accept in this case end behavior. I would accept in this case horizontal asymptote. They're both fine. I'll let you know when we have to be careful about being specific and differentiating the two. But for right now, we'll just leave it at that. Is that okay with everybody? Okay. So if we want to try to find these asymptotes, what are some of the ways that I could, like find, say, the vertical asymptotes? Anybody remember how we could do that, or how we do that? Keely? Okay, so you first want to start by factoring. Okay, and then what? So let's say that we had this problem that we started with. So you say to factor that as our first step. We'll kind of maybe work through it, and people start remembering the steps that we need to worry about as we do that. So let's look at the numerator first. How do we factor that numerator? So how does that numerator factor? What was that? So you need two numbers that multiply to give you -3 and add to give you +3. So what do we say then? Brockton, what'd you say? It can be factored over the rational numbers. This one is probably really as good as we need, or good as we can do, is the way it's written. Now, you could factor this, but it probably has irrational factors involved, which is not going to be worth bothering with if we're dealing with looking for vertical asymptotes here. How about the denominator? How does that factor? Good. So x plus 3 and x minus 1. Okay, so Keely said, first maybe we want to start by factoring this thing. So we factored it. Then what do we want to do next? The solutions to what? That's a good idea. Be a little bit more specific for me, though. Okay, so James is saying set the denominator equal to 0 and solve. I agree with that in this case, although there should be a second step that we need to be a little bit cautious of that didn't have to happen for this particular problem, but you would need to be careful about in general. What was that? Okay, I think that's kind of on the right track. You need to make sure you've reduced this, because just setting the denominator equal to 0 and solving without checking to see if you reduce, some of those solutions the denominator set equal to 0 could be removable discontinuities and not vertical asymptotes. If you've done all your reducing, everything left would be a vertical asymptote. But if you don't reduce first, if possible, you might have removable discontinuities there still mixed in with your vertical asymptotes. Does that ring a bell? Maybe. I know it's been a long day. Try to wake up a little bit. Okay. Oh, before we talk about the HAs though, what's another way you could find these vertical asymptotes that doesn't require you to actually do any algebra? Allison? Yeah, you could graph and trace, or you could look at the XY table after you've graphed the function and just look for the places where it's undefined. Visually, it's not hard to use your calculator to kind of pick out those vertical asymptotes, right? Everybody agree with that? Okay. How about the horizontal asymptotes? This was a little bit more complicated. Does anybody remember kind of what this involved, even if you don't remember the specific rules for how to do it? Maya? So there are 3 different situations that we can run into, but we're not worried about the denominator set equal to 0 per se for this part. What we're concerned with is the degrees of the numerator and denominator. So the 3 situations we might run into is when the degree of the numerator is greater than the degree of the denominator, when they're equal, and when it's less. When the degree of the numerator is greater than the degree of the denominator, that's when you get the slant asymptote. When they're equal, you get a horizontal asymptote or end behavior, but for right now, we're just going to call that an asymptote. That you can find by looking at the leading coefficient of the numerator over the leading coefficient of the denominator. And in the last situation, you get an asymptote or end behavior at y equals 0. Let's go back and look at the example that I graphed here at the very beginning of the lesson. I'll give everybody a minute that's copying stuff down to finish kind of copying stuff down, but I'm going to scroll back up and look at that graph that we drew at the very beginning of this asymptote section. LC is leading coefficient, is what I've abbreviated there. But good guess with least common would be another appropriate LC that we've used that phrase certainly a bunch of times. But we're looking for leading coefficient there for LC. All right. So if I go back and I look at this problem that I've written here, I notice, what is the degree of the numerator? Numerator is this. What's the degree there? When we talk about the degree of a polynomial, we mean the biggest exponent on the variable. So the degree of the numerator is 2. What's the degree in the denominator? Also 2. And as James said there, they're definitely equal. They're both degree 2 polynomials. So my horizontal asymptote will be the leading coefficient of the numerator. That's 1 over the leading coefficient of the denominator. That's 1. And what do we see in the graph that our asymptote-ish thing is? Y equals 1. Everybody ring a little bit of a bell here as we kind of go through this. Again, wouldn't expect you to have those rules memorized. What other way could you check for horizontal asymptotes? Use the graphing calculator, yeah. So if I fire that bad boy up, I'm going to just type in this function exactly as it's written. Probably the easiest way to do that is to use the fraction options. We can open the fractions menu in our calculator by pressing alpha and y equals. And then I'm just going to use the numerator over denominator option. And that's a little bit easier, I think, than dealing with having to use a bunch of parentheses to get this to do what you want it to. And I think probably everybody has a calculator that's new enough that they still have that fraction option built into it and that menu shortcut built into it. If you have actual physical AAA batteries in your calculator, depending on how old it is, it might not have that option. But if you have the rechargeable calculator, I think for sure you have that option and that shortcut built in. So if I look at this on my standard window, so if I look at the ends, there definitely appears to be some like asymptotic behavior, right? It looks like we're almost horizontal at the ends of our graph. Everybody agree with that? To check that, what I'm going to do is I'm going to do second and then the window button and look at my table. So I'm going to look first at the very far right end of the graph. So I'm going to start my table starting at 1,000. If I look at that, those values out by 1,000 are almost 1. If I do the same thing and then look at negative 1,000 and look at my table, those values are almost 1. So at this point, I'm pretty sure that what I'm looking at is a horizontal asymptote at y equals 1, even if I couldn't remember the rule for how to do it without having to look at the graph. So that'll wrap up today.